Cool. Hey everyone. Excited to get started. Yeah, today we're going to talk about Iceberg, which is one of my favorite topics to talk about. It's something that I think that a lot of people have nowadays heard of, but maybe haven't really gone deep in understanding, especially from the perspective of machine learning, where Iceberg does unlock a ton of use cases. Um, but it's kind of can be hard when you look at what Iceberg does, you Google what it allows for to kind of map those things onto a machine learning workflow. And it also doesn't always clear how to get started. So what I'm going to do today is I'm going to kind of go with a more pragmatic approach of starting with how data used to work, kind of like rolling back time and building up from the data lake to the data warehouse to the lakehouse architecture and Iceberg specifically. So I'm going to kind of build up to that and talk about why design decisions were made so that it can be a little easier to understand Iceberg in the context of a kind of larger data engineering wave that's been happening. And yeah, I'm going to end with talking about how it kind of fits into feature stores and the like. Um, so yeah, let's get started. Um, so I'm going to share my screen. Just give me a moment here. Just moving one thing over so I can get this to work correctly. Okay. Okay, so I'm going to share my screen here. If you have any questions, by the way, during this talk, you can throw it in Zoom if you're on Zoom. And if you are on LinkedIn or somewhere else, you can also just throw it in there. Let's get started. So I'm not sure why it's not letting me share. There it is. Okay, I think that's working. Awesome. Let's talk about the data problem in machine learning. Uh, Looking at this, you'll kind of find that this isn't just a machine learning specific problem, but again, I'll be really coming in from the perspective of a data scientist or someone doing machine learning. One is building your training data. You're working with and across massive data sets. You have data that's likely across organizations. You might have like marketing data and product data. You often are dealing with dirty data, just with the nature of enterprise data. You need to find this data. You need to figure out how it was built. You might need versioning, lineage, etc. And then finally, in machine learning, it's quite common to have to work with streaming data and low latency data. So for example, for things like fraud detection or recommender systems, that becomes top of mind. So I'm going to go back, like I said, I'm going to start by going back in time and talking through the different big things that happened that enabled and kind of led to the creation of Iceberg. First, starting with how data used to be, the data silo. Um, Not that long ago, actually, like most data was just kind of in different databases. You'd have Postgres or similar databases all over. There'd be your CRM database, there'd be your ERP database. You'd have different databases for different applications, and you'd have these silos. And so if you're gonna try to um, join data across these different silos, it was quite difficult. You would have to maybe query those things directly, maybe download them as like CSVs or similar and work with them that way. It wasn't really possible all the time and definitely not easy to build models. It also doesn't help that in a lot of these situations, the databases were also transactional or OLTP databases where they were actually sometimes being used in production. So it was painful. So this kind of led to the idea of the data lake. Data lake was a pretty simple concept. Why don't we just take all of our databases, all the data we have, and just kind of dump it into one place so that there's one place where all of our data exists. This is the data lake. Um, it- Looking back, it's very it seems really simple. Like just cool, let's just dump everything in S3. It also seems kind of like a bad idea because we realize now how painful it is to work with something like this. But at the time, it was actually very enabling. It enabled use cases like BI and other things that weren't really possible before because all your databases were in like 1,000 different places. So it centralized all the data. It was with the rise of things like S3 of object storage. It was also pretty low price. But the cons, it was still hard to find your data. Like even though your data was in one place, it was just kind of all over the place. This kind of blasted through a bucket. You had data of many different types of formats. It was still pretty slow to work with these data sets, even though now you could do things like joins. It was not easy to work with. Uh, you couldn't really do streaming data, versioning data, etc. You could kind of hack your own versions of this stuff on top, but it wouldn't really be the same across your different data sets. For example, if I have transaction data, like what people are buying, I might have it in Postgres. Maybe every 24 hours, I dump it into S3. Um, I could dump the whole database every 24 hours. I could dump a diff every 24 hours. And when you think of the diff, you start thinking about, okay, well, I'll just append a new file every 24 hours of the diff. Then you start worrying about, well, how do I handle deletions? How do I handle all this other stuff? Nowadays, we have to worry about GDPR. It's not easy to work with. And then on top of all of that, because the data is in all these different formats, you don't really get a SQL interface. You kind of have to write pretty low level Spark or similar code to be able to interact with this data. So that was the idea of the data lake. Let's just centralize things. Moving forward, the next kind of big advent in data engineering, the big change in data architecture was the data warehouse. Snowflake was a big component here, like a big driver of the data warehouse. And the data warehouse idea, kind of similar to the data lake, let's just dump all of our stuff into one place. But this time, rather than just it being kind of almost like a file system where we just have all of our stuff in one place, let's put it into tables, relational tables, and let's attach compute to it so that we can just query these tables directly. And uh, the other benefit is because it's relational tables, because indexing exists in Snowflake and data warehouses, we can do much faster queries. Where before the data lake, you had it was just much harder to work with and slow. With Snowflake, it became possible to ask a question like how many users went on my site in the last 24 hours and be able to get that immediately. So the pros, it's table oriented, it's relational, natively supports SQL. It tends to be more expensive than the data lake. It's not, things are changing here, but it still tends to be more expensive, and it's just because it's not always stored in the same way that it would be in a data lake. You don't have just an S3 bucket that just you dump everything in. Lots of times, because it's faster, it will actually keep a lot more data live. It'll have a lot of compute that's just constantly running. It's also less flexible in a way because you're forcing yourself into this table format. So for certain use cases like images and audio, it's just not as good. But I'm going to ignore those use cases for this talk because and just assume that most of your data more or less fits in table format. At most, it's going to be like a text column, but I'm going to ignore the rest. So we can almost ignore that con for now, but it's important to understand. Okay, so we have this idea of a data warehouse. We have this idea of a data lake. Um, they both have pros and cons. The pros, the data warehouse kind of feels like the better interface. You can use SQL, you have tables. The data lake allows for much larger data sets. It's much cheaper to use. It's kind of in S3, which allows you to plug any sort of compute onto it, unlike something like Snowflake, where it's all sort of in their proprietary walled garden. So the idea was, how do we put these things together? And like I said, it allows data to be stored at rest in S3. It supports tabular data and it allows you to run SQL queries and the like on tables. So the first thing we need to do is unify the file format. We want a file format that is inherently columnar, so it looks like a table to start with. And so the most common by far format is Parquet. So the short of what a Parquet file is it's really just a file that allows for columns, schemas, etc. One of the things in Parquet that is also really interesting, was a kind of really interesting design decision, is the idea of a column layout. The realization was when working with analytical data, like in this situation, one is you typically work on a handful of columns at a time. If you have a row which has 1,000 columns, and you want to just, let's say, take the average of column A, like in this situation, I just want to take the average of column A. In the row layout, I'd have to go through pretty much the entire file to take an average of column A. In the column layout, all of the values of column A are actually put together. So rather than going, row one, row two, row three, it actually shows the whole column of one, then the whole column of two, etc. Not exactly. They actually like break it out. They chunk it up a bit, but that's kind of how you can think about it. So, okay, now we have this file format. The file format is optimized for SQL queries and the like. And it's something that everyone can kind of standardize on. It looks like a table. This isn't quite enough because we need to think about situations like appending data. Like I want to add a few rows to this Parquet file. With things like S3, you can't really just append to a file. Files are immutable once they exist. And these Parquet files can be relatively large. So it doesn't really make sense if I'm adding 3 rows to have to rewrite the entire file plus 3 rows. What I would rather do is kind of append maybe a new file. So I have file one, which is my initial, and file two, which is the few rows I added, and I can kind of work that way. So you kind of want something on top of Parquet to give this concept of a table format built on Parquet. The first example of this was Hive. With Hive stores its metadata in pretty much if you use the Hive metastore, it's actually being stored in a SQL database. And it points at the directory of the table. That table can be broken up into subpartitions, which allows for indexing. And then those partitions will have multiple Parquet files. So it gets a little more complicated than this, but not really that much more. But what Hive allowed for is, for once, we finally have these table formats. We actually are able to have something that looks like a table that also things like Spark and our processing engines are aware of and are able to query directly as tables and run SQL on. So we went from this data lake idea where we just stuff data into. By creating this table abstraction, we can actually have Hive plus Spark kind of looks like a data warehouse. With the big difference being that the data is all in S3. It looks like a data lake that is structured. So this was a huge one. And this kind of is the start of what we now call the data lakehouse. But Hive is kind of, it's pretty simple. And a lot of work went into how do we build a better table format specification? Like, how do we take this Parquet file and how do we put them together in a way that is better than just having, a directory of directories where we just shove data? It's really important when you start thinking of things like deletes, which in Hive, you'd actually have to delete the file. If you're deleting a few rows, you'd have to rewrite the entire file. You start worrying about things like versioning. You start worrying about things like consistency, where with Hive, making sure your table is consistent when you have multiple writers can be really complicated. So Netflix came up with the table format, which they eventually open sourced and is Iceberg. I'm going to go into a few specific parts of Iceberg. I'm going to kind of break down how Iceberg works, how it's different. And I'm going to really go through three things that it enables. One is snapshots and incremental changes. In Iceberg, every time you write data, and that's a simple case, so we'll talk about that one. When you write data, it doesn't actually delete anything or change a file. So if file A had rows 1 through 100 and you added another row 101, it's not going to delete this file and create a new file. It's actually just going to create another file next to it. And it will maintain metadata, which I'll get into, which would actually allow you to go back to the old format. So if you point at the old files, it lets you go back in time. Let me try to make this even more clear. If I have a file which has number of participants in this call. When I joined, and I was the first one to call, it created a new Parquet file, which was participants, and it would just have one row, which is Simba. It would also create a metadata file and point at that one data file. So it says snapshot 1 is just this one data file. Then Marie joined. And so now there's a new data file. And then there was another metadata file that was created, which is snapshot 2. Snapshot 2 points at both the initial file with my name in it and the file with Marie's name in it. So every time data changes in any way, rather than actually deleting and replacing data, we're just appending data. And it creates this set of snapshots. And so that example I gave of the pointers and manifest and metadata files is actually more or less how it works. A little more complicated. There's a few more layers of abstraction, which I'll break into. At the bottom, you can choose what kind of file format, but most people use Parquet. So we have all these files. Above it, we have manifest files and manifest lists. So manifest files kind of just take a few data files, point them together and say, hey, this is a chunk of data. The manifest lists point at a few manifest files, which is like, hey, these manifest together. So these chunks of files or sets of files together make up the table or make up a change, really. Above that, we have metadata files. Metadata files are actually where the snapshots kind of happen. So metadata file 1 was the first thing. We had S0. So it pointed at manifest list S0 and said, this is the table at the snapshot. When I added new data, it created a new manifest list. And then I created a new metadata file, which is snapshot 2. Snapshot 2 has S0 and S1. We also have a catalog, something like AWS Glue or similar at the top. All that does is it just points at the most recent metadata file. That's all. It also typically has some form of locking so that you can have a consistent view of what the table looks like right now. That's Iceberg in a nutshell. It is the ability to, when you change a table, when you add new data, delete rows, whatever, to have these sort of diffs that get created and added. And you end up with this kind of infinite history that gets created as well. So that allows you to do a query. Like I can query, if I wanted to query how data looked like at a point in time, I can go through all the metadata files and I can find a metadata file that was active, that was the version at a certain point in time. And I can go through the manifest list and manifest files and actually get a view. I can query a table like it used to look like, which is a really valuable idea, especially in machine learning, where I might want to train data how it looked like at a point in time. So I can use Iceberg to accomplish that. The other thing it allows you to do, which is interesting, is you can create branches and tags, and you can really go deep on this. You can treat this like a Git workflow where you can append data, which creates a new metadata file, but not make that metadata file the current one. And so you can actually create forks of data in a table. So this abstraction is really powerful. But the simplest part of it is the snapshots, ability to roll back. If something goes wrong, you can go back in time and you can put your table in the format it used to look like. The second really powerful thing, especially for machine learning, is the idea of a merge on read. In a lot of situations of ML, you're writing data into like a feature store or something similar a lot more than you're reading it. So every transaction might be updating the, your feature table, but you might only read that table when you're training. So we have the idea of a merge on read. With a merge on read, what we do is if we have a file, data one on the left here, that has some keys and values. When we update the data set, what we typically do, which the generic way to handle this is called a copy on write. With a copy on write, if we deleted, let's say we deleted a row. So we deleted row 1, Jack Apple. And we really overrode it to be Jack Banana. What we would do in the copy on write is you take data 1. In Iceberg, you wouldn't delete the file. What you do is you create a new file, call it data 2, which has all of data 1, but with the rows that you changed. In the metadata, you just point out data 2 as opposed to data 1, and you accomplish a new snapshot. With merge on read, what you do is you write the diff. So you write new data that was created, any rows or similar that were deleted, and you have a diff. So if I want to get table version 2, in copy on write, I just read data 2 because it'll have all the data in it. With merge on read, what you would do is you would read data 1, and you'd read data 2 and everything in table version 2 and kind of join them together. You'd compact them, and that would form the new table version. So the benefit here, like I said, is as you're writing data, you can just write diffs. And when you read the data, you can join all those diffs together to kind of rebuild the table, as opposed to every time I stream data into this table, I have to rewrite all of the files that were changed, which is typically how this would work. So it's really powerful. You have to use it in the right places. If you use it in the wrong place, what happens is reads become extremely expensive. So even though the write is cheap, every time you read, you have to take all these different files and kind of like compute them together. With copy on write, what you're doing is you're making the write more expensive because you have to copy and create these files. But the read is super cheap because the file in its full format is there. So on copy on write, you wouldn't have that data 2 delete 1. You'd have data 1 and data 3. With merge on read, you create the diffs, and then you put them together to build a new table. So that's merge on read. This makes feature updates, feature writes really cheap and allows you to kind of, when you do a materialization or similar, you can kind of compute the new version of the feature table. The final bit, and this is probably, in my opinion, the most powerful thing it does, the push down predicates. Because we have those manifest lists we talked about, those manifest files that point at the data files. Those manifests aren't just dumb pointers of like, hey, these 10 files are part of my partition of data. You can have metadata in it. For example, you can say that these chunks of files are part of my, are my partition. And the first row in here starts with A, and the last row starts with C. So if I do a query, and I'm only want to know about people whose, let's say, names end with or start with J, I can skip all of those data files because I know that they start from A and end at C. It's an index. Like I can build these indices so that I can run queries and not have to read all my data in. Um, with the data lake, you definitely have to do that. And even with Hive, if I run a query, that metadata isn't there. Those kind of the idea partitioning in that way didn't really happen. So the query engines would oftentimes have to read all of the data at once, which was really expensive. If I'm doing a join, this is another really good use case is a join, which in ML, super common. With a join, I could say that, again, let's say I'm using first name as, or name as the joining key. And I have two tables I'm joining. And in both tables, I do that same thing where I store them sorted from A to Z. And I want to join these together. If I didn't have that index, I would have to read everything from both tables. I would shuffle them around so that files that were, between A to C were on the same node so that each node could do the join themselves. Here, because I already have it pre-sorted when I wrote it, and I have that metadata, I can read, A for C, users A for C from both tables into one node immediately. I don't have to read them all, sort them, and then kind of shuffle them to different nodes. So joining becomes way cheaper. With some of our customers, we've seen it drop like 97%. So it's dramatic when you set up your indices correctly. And the other really powerful part of this is you can really tune how you do that. You can tune what you sort by. There's different types of indices and sortings you can do. So you can really put your table in the perfect format when you write so that when you run these queries afterwards, it works really quickly. You can also combine these things of like merge on read and other things. You can really put a lot of this stuff together to have a perfectly optimal table format for whatever use case you have. So Iceberg's super powerful. We talked about, time travel and snapshots. We've talked about how it handles streaming data and deltas. We've talked about push down predicates and indices, but it doesn't come without cons. One is managing tables. Every time you write, like in that streaming example I gave, you're creating a lot of small files. You're going to want to compact them from time to time. There's other optimizations you want to do. Pretty much every time you're writing, you're creating new metadata files, you're creating new data files. The benefit is you have, a billion snapshots, but you might want to compact them. So like I only want the snapshots of the last 30 days, and that will make your table way more optimized. But it's your job to set up that compaction and to set up the optimizations and have the right level of snapshotting and other things. Two is you have, like I mentioned, like you can build a whole Git workflow, like a Git for a table in Iceberg. But the way to do that, you're working with pretty low level primitives. These are not, yeah, you're working at a quite low level. And so it's not easy, is a short. Like you really have to understand Iceberg. And not only do you have to understand it, you have to somehow get this across to all users or build tools and abstractions above Iceberg to have your workflow. And then finally, if you end up going for the Iceberg docs, you'll find that there are hundreds of tuning options and options for your tables. They can all be changed. Like you can change the size of a file. You can change or the size of, yeah, like a data file in Iceberg. You can change how many files exist in a single metadata file or should exist in a single metadata file. You can change how big each chunk in the parquet is. There's just all these things you can tweak, and they all have like effects. And knowing which ones to pull, which ones to tune, is not easy. It is quite complicated, actually. Um, the idea that we had a feature form was to take the power of Iceberg and to build a workflow on top of it that has that Git like format has all the benefits of Iceberg, but kind of abstract away Iceberg a bit. Originally a feature form. So feature form is a way to build your data pipelines for machine learning. So not dissimilar to, yeah, you're building data pipelines for machine learning. Originally, how it worked is we had different implementation for Spark, for Snowflake, for ClickHouse, for BigQuery, all of our different things we supported. We had specialized implementations, but because of how things worked, it could be pretty slow, especially at massive data sets. Like for petabytes of data, it started to kind of come up to a wall. It just couldn't handle that much data. And then it forced data scientists, data engineers to implement all those tuning options that we talked about. They had to figure them out themselves. So we've recently rewritten feature form entirely on Iceberg. So even if you're using Snowflake or ClickHouse or BigQuery or Spark, all of these things actually support reading and writing Iceberg into S3 or wherever else. So with feature form, as you're building your feature pipelines, you can still work in your own Spark, Snowflake, etc. But under the hood, feature form is actually creating Iceberg tables and tuning them and building these tunings in a way that is generic. So we've learned the best way to tune these tables for machine learning workflows, and we do that automatically for you. It allowed us to unify our stream processing and batch processing. All the things that we talked about of what Iceberg allowed for, we were able to get those values and build a workflow on top specifically for machine learning. And the most powerful thing, in my opinion, is a user of feature form doesn't have to know everything about Iceberg. They can just define their features as SQL, as PySpark, etc., and know that under the hood, it's building these Iceberg tables, it's putting them into Unity Catalog or Glue or whatever you use. It's materializing into Redis or Dynamo. It does everything that that a specialized data engineer would do. Like if I sat and hand tuned every single one of these pipelines, but all you have to do is give it a SQL query or PySpark code. Featureform is open source, and you can find this on GitHub. You can play around with it, and you can get a feel for these things. I hope this was useful. I'm going to stop here and open it up for any questions. If anyone has any questions about Iceberg, about Featureform, about anything, happy to go through it. Give a second. Again, you can throw in Q&A if you're on Zoom, and if you are on LinkedIn or I don't know if we post on Twitter anymore, but if you're on LinkedIn, you can leave a comment there, and Marie will be looking there. Anything on LinkedIn, Marie?
Nothing on LinkedIn.
Cool. I'll take that as I did a good job explaining. Oh, there's one here on Zoom. How performant is Iceberg? It's a hard question to answer just because it really depends on how you use it. What Iceberg gives you is all the knobs you'd want to tune to be able to achieve the performance you'd want. For example, if you wanted, you could compact every time you wrote to Iceberg. And if you set up your indices correctly and your partitioning correctly, it would be about as optimal as you could get with Parquet files. So you can get it to be extremely fast. If you don't compact well and you don't optimize the table well, it can actually be slower than just using Hive, which I've also seen happen. In practice, just using Iceberg and building proper partitioning and indices, especially if you're coming from like just dumping Parquet files in S3, is going to be significantly faster. For some of our customers, even just putting Iceberg on and adding basic indexing and basic optimizations for an expensive join, would make it 10 times faster. And that just again comes from the ability for Spark to be able to look at an Iceberg table, look at the partitions, and properly do join and where clause without having to actually read all of the data across all the different nodes. Most people use Iceberg for performance. So it is very performant, but it also has all the other things we talked about, like snapshotting, etc., which makes it very flexible to use and allows you to handle a lot of situations that can happen in data engineering, like dirty data coming into a table, etc. Cool. If there's any more questions, feel free to put them in Q&A. I'll answer them if they come up, but I'm gonna pass it to Marie to talk about what happens now.
Thank you guys so much for watching the webinar. After this, I'll send you guys an email. It'll have the recording of this webinar if you want to come back and review stuff. It'll also have links to our open source if you want to test it out. And our Slack community if you have any questions about MLOps things, feature store things, Iceberg things. And then lastly, feel free to let us know if you have any feedback. You can respond to that email.
Great. Thanks, Marie. I don't see any more questions, so I'm gonna assume we're good